In this question, it says, in the lab, a scientist mixes together 25 grams of chromium oxide and 25 grams of a different chromium oxide to isolate yet another chromium oxide. So you can practice naming these, and you should. If the scientists were only able to isolate 25 grams of chromium dioxide, use the balanced equation to complete the following table. So this is a limiting reactant question, so the first thing I'm actually going to do is determine the molecular weight for each and every one of these. So chromium's molecular weight is 52, and oxygen is 16. So these molecular weights are going to be as follows: 152, 100, 84, and 32. So the reason I did that first is so that as we set these up, we can actually use these quite quickly. So I'm going to start with the CrO3. So we have 25 grams of CrO3. We're going to convert that to moles using 100 grams and 1 mole of CrO3. From here, we need to convert to grams of the other chromium oxide. So there's 3 moles of chromium oxide for every 1 mole of chromium oxide. And so in 1 mole of the other chromium oxide, there are 152 grams. And so when I plug this into my calculator, I get 12.67 grams of Cr2O3, and this is required. So this calculation right here can identify our limiting reactant because we need 12.67 grams of chromium oxide, Cr2O3, but we have 25 grams. So let's double check on the other direction just to make sure. So we're going to take our 25 grams of Cr2O3, convert that to moles with 152 grams in 1 mole, and it is 1 mole times 3 moles of CrO3. For every 1 mole of CrO3, there are 100 grams, and this gives you 49.34 grams required. And we only have 25 grams. This tells us that this is our limiting reactant. So CrO3 is the limiting reactant. So the next questions are about the excess reagent. So if something is the limiting reactant, it is completely consumed. Therefore, there is 0.00 grams of CrO3 left. For the other, we're going to subtract what we have minus what is required. So that would be 25.00 minus 12.67 grams, and that's going to give us 12.33 grams. So now we're going to calculate the theoretical yield of oxygen. We are also going to add in another box for the yield of CrO2, since we will need that in the last part of the box that is provided for the percent yield. So to calculate the amount that is used, the amount that produced, we're going to take our limiting reactant of 25.00 grams of CrO3, divide that by 100 grams in 1 mole. So for every 3 moles of CrO3, there are 5 moles of CrO2. Move things around a little bit. Sorry for the jiggling. For every 1 mole of this, we have 84 grams. And so the yield for this is going to equal is 35 grams. And so the yield for oxygen, we're going to take our 25.00 grams of CrO3. And again, there's still 100 grams in 1 mole. There are still 3 moles of CrO3 for every 1 mole of O2 produced. 1 mole of O2 is 32.00 grams in 1 mole. In this, there's 2.66 grams. That needs 1 more sig fig. Let me look that up. And it's 0.667, so we'll just add that right on in there, and it's 2.667. So the last part of this asks asks about percent yield. And this is the actual divided by the theoretical. And so we actually collected 25 grams, and we could have gotten 35.00. If you multiply that by 100, I get 71.4% yield. So don't forget, in the limiting reactant problem, the first thing I recommend is determining all of your molar masses. This is going to allow you to easily conduct the calculations to determine how much is required. So this is how you would look at a limiting reactant problem.